All right, so here's the last lesson notes on area and polar coordinates. I'm going to go through how to do this kind of stuff on the video. If you want to know where it came from, we'll talk about it a little bit in class. You can also look it up in your book. But right now, this video is going to primarily be how to use these formulas. So, excuse my weird voice today, I have a cold. Area and polar coordinates. So the area between the region, the area of the region between the origin and the curve in polar coordinates is the integral from alpha to beta of 1/2 r squared d theta, where r is the equation of the polar curve. And if you're bound between two polar curves, then you square first and then subtract 1/2 r1 squared minus r2 squared. So basically what we have to do is figure out what our angles are that we're bound between, and those become our limits of integration. So let's talk about it. So the first one, find the area of the dimpled limacon, r equals 3 plus 2 sine theta. And if I bring up the calculator here, just to give you an idea of what we're looking at, we are looking at this thing right here. If I can get it to drag over. So it's this thing right here. It's a dimpled limacon, kind of looks like a lima bean. And if we want to find the area of that thing, we need to use the formula. So our formula is find the integral of 1/2 r squared theta d theta. So 1/2 r squared d theta. Now I need to figure out what my bounds are. Now if you're going to do the whole thing, it's either going to be 0 to pi or 0 to 2 pi in many instances, and you just have to figure out how many of those things graph. So if I pull the calculator back up and I go to y equals and I make sure my turtle tracer is on and I hit graph again, if we watch it graph, there it goes around once, 0 to 2 pi, and it stops. It does not duplicate. So this goes from 0 to 2 pi. If that had gone around twice, I would just do 0 to pi. So I have the integral of 1/2 3 plus 2 sine theta d theta. And then I can, from there do math 9. I'm going to do the integral from 0 to 2 pi of 1/2 r squared d theta. And I am in polar mode, so that looks exactly like it should look. And I hit enter, 34.5575. And there's the area. Okay, so that obviously was not that hard. Now let's try to get to the ones where you really have to do some more work. So find the area inside the smaller loop of the limacon 2 cos theta plus 1. So I'm going to do the same thing here. I'm going to go into y equals, what was that, 2 cos theta plus 1? So 2 cos theta plus 1. I'm going to graph it. Alright, so it goes around once, and there's definitely a little loop in there. I'm going to zoom in a bit. So I want the area of that loop. Well, if you look at the loop, if I look at that loop there, I need to figure out where it starts and stops. So if I look at it, it starts and stops right on the origin. So what I want to do for that one is I had r equals 2 cos theta plus 1. I want to set that equal to 0 to figure out when it hits the origin. So if I set that equal to 0, I have cos theta equals -1/2. And then because I know my trig equations, I know that theta equals 1/2 at a reference angle of pi over 3, but I need to be in quadrants 2 and 3, which is going to make this 2 pi over 3 and 4 pi over 3. So at 2 pi over 3 is the first time it hits, and at 4 pi over 3 is the second time it hits. And then if I integrate in that window, That's going to give me the dimpled part of the lemmasol. So I want the integral from 2 pi over 3 to 4 pi over 3 of 1/2 r squared d theta. So again, I'm going to pull up the calculator, and I'm still in polar, so I can use my home screen here. I need, let's see, math 9, pi over 3, nope, 2 pi over 3, 2 pi over 3, and 4 pi over 3. I put them in the wrong spot. Sorry. 4 pi over 3, there we go. 2 pi over 3. Oh my goodness, move over. Come on. There we go. Wow. 0.5 r squared d theta. Whew. Da-da-da. 0.5435. Okay. Not a big deal so far. So let me shift this up a little bit so I can see the next one. Alright, find the area of one petal of the rose curve, 2 sine 4 theta. Okay, yet again I gotta pull the calculator up. So if I do y equals 2 sine 4 theta, I'm just going to graph it, see if it fits in here. Look at that, it does. That looks a little choppy. I'm going to change my window a little bit and just change this theta step to like 0.08. If you ever notice that it's not smooth looking, feel free to do that. I'll clean it up a little bit. It's beautiful. I have 8 petals. So, I have 8 petals from 0 to 2 pi, which means one of the petals, which should graph from 2 pi divided by 8, which is pi over 4. So I'm going to quickly just make sure I'm right there, and I am going to graph on the window from 0 to theta equals pi over 4, and make sure I see a whole petal. Alright, now, Mrs. Ripper, why don't you see a whole petal? Well, it's because our calculator theta step is still kind of big, so if I go back and I were to change this to like 0.01, it should get a little bit closer there. Oh my gosh. It's like watching paint dry. There we go. See, there's one petal. So your theta step was kind of messing up, but I do get one petal from 0 to pi over 4. So if I want the area of one petal, I can do the integral from 0 to pi over 4 of 1/2 r squared d theta. What do you think, Miss Viver? This actually isn't so bad. Yeah, just wait. It gets kind of nasty later on. So, again, I'm actually going to do second enter here. And then second left will bring you all the way to the left-hand side. So, if I change this to pi over 4 and 0, actually. 0 and pi over 4. Ignore the dinging. Sorry, that's my phone. And 0.5 r squared, yeah, everything else is good. And I changed my y equals to my new r, beautiful. So if I hit enter, I should get the right answer. 0.785, sure, that seems reasonable. Ta-da! Alright, here's where things get interesting in these last two, so kind of stay with me here. So, let's graph it. R equals 1 and R equals 2 sine theta. So R equals 1 should be a circle centered at the origin with a radius of 1. And then 2 sine theta is going to be another circle, not centered at the origin, but also with a radius of 1. Oh, whoa, I have that theta step really small. Let me hit on and change that. Now, I could go back and edit this out, but I really want you guys to see that, wait, if it's going too long, I have a problem, and I want to change this to 0 to 2 pi all the time. If you don't want to have to go back and change that manually, you can always hit zoom 6, and that will put you in a standard viewing window. Mrs. Viver, that doesn't look like a circle. That looks like an ellipse. Well, if that's bothering you, you can hit zoom square. And zoom square will square it out so that everything looks like it should look in the real world when, if you had a square viewing window. So look at that. Beautiful. Much better. So we want the area shared by those two circles. So I want, should be down here, I want this. Come here. Dragging this is not as easy as it looks. I want this region right in here. Now, one of the things we can do with Polar to help ourselves is I can go back to here, I can hit mode, and if you put yourself in simultaneous, it helps figure out when these two things cross. So if I hit graph again, notice when they're together, when they intersect, the red curve is outside the blue curve, and it looks like the red curve went around twice. So I'm actually going to go back to my y equals. I'm going to change this guy to a key. Mine obviously does that differently than yours does. I'm going to hit OK. And I'm going to graph it again. So there they cross once, and there they cross again, and then it crosses yet another time. So if I want that region in between, when they first cross, they hit here, and then this is outside, and then they cross again. So if I were to do an integral of red minus blue, I get this outer portion, not the inner portion. So the tough thing is here, when things are bound by two curves, you can't assume what's outside and inside. You have to look at the math behind it and look at the angles behind it, which is relatively obnoxious. I totally get that, but you just kind of have to do your best here. So to figure out where they intersect, I'm just going to do it by hand and say I have 1 equals 2 sine theta. So sine theta equals a half. So theta equals pi over 6 and 5 pi over 6. And that means right here and right here corresponds with pi over 6 and 5 pi over 6. So if I do the integral from pi over 6 to 5 pi over 6, 6, of 1/2 outer r squared, which would be the red in this case, minus inner r squared d theta, I'm going to get this region out here. Okay? Even if I reverse the order of these, I'd have a problem because honestly I'd get a negative, because you can't get this black area directly, because when those intersect again, once they intersect, the red is outside the blue. So that's just what you got. That's just how you have to deal with it. So I have pi over 6 and 5 pi over 6. This will get me that stripy area. So if I do it in the calculator real quick, I'm going to have, let's see, math 9. I know it's boring watching me do this in the calculator. Pi over 6, 5 pi over 6 of 0.5. And then, let's see. I don't remember which one came first. Let me check here. The 2 sine theta is R2. Oh, man. Shove me way to the front again. Oh, Mrs. Bibber, it's boring watching you do this. I know, I know. Here, I'll sing a song. I don't know what song to sing now. This is the song that doesn't end. It goes on and on, my friend. Some people started singing it, not knowing what it was. It keeps on going on forever, forever, just because. Okay, I'm bored with that song now. There we go. It's from a show called Lamb Chop, if I'm not mistaken. That's before your time. Alright, 1.913. All that for 1.913. Fine. Now, I really wanted the black part. Well, let's just think about math here for a second. That red thing's a circle, right? It's a circle with a radius of 1. I can tell that by looking at it, and you can do it with some math that I don't feel like showing you here. But that's a circle. It's got a radius of 1, because it intersects right here at 1, and here at 0. So it's a circle with a radius of 1. Just trust me. So the area of the red circle is pi r squared, which is pi. That's the area of this whole thing. I also know the area of this, and if I take their difference, I would get the black scribbly thing. So pi minus 1.913 is going to be pi minus answer 1.228. And that is the area that I really want. Okie dokie. Alright, I want to do another one of those where quick pause. I want you to give a shot at number 5, and then we'll come back and go through it together. I know this is getting long. Just, hang in there. This is the last video. Please, please. Pause, try number 5, and then come back. I'm resuming this for a second just to show you what it graphed like, and then I'm going to pause it on my end again to show you the math behind it, but I do want to show you the graph. So when I graph r equals 2 and 3 plus 2 cos theta, and I hit graph, and I look at how they look, oh, my window doesn't work. Hang on. Alright, I'm going to zoom 6 my window here. There we go. They intersect once over there, then they intersect again down there, and they both graph from 0 to 2 pi. So this guy is on the outside, and that guy is on the inside until they intersect. So I know they intersect here, and this whole time this guy is outside and that guy is inside. And if you look at it, it's symmetric. So when I set that up, I'm going to use that as part of setting up my polar curve here. So I need to figure out where they intersect. So 2 equals 3 plus 2 cos theta. So negative 1/2 equals cos theta. So theta is going to be, what's that going to be? 5 pi over 3? No, 2 pi over 3, pardon me. 2 pi over 3. So this is 2 pi over 3 right here. So I need the integral from 0 to 2 pi over 3 of my outer r, which is the limacon, and that's going to be 3 plus 2 cos theta minus the inner r, which is 2, d theta, and that should get me this stuff. And then, since I need that doubled, I'm going to multiply it by 2, and that should give me my answer. So, let me try and do it real quick. So, quit, math, 9, 0 to 2 pi over 3 of, let's see, vars, y vars, nope, not parametric. Sorry, it's a lot of calculator nonsense today in this video. Get on your game. This is over vars, y vars, polar r1 squared minus vars, y vars, polar r2 squared. And then I should be able to hit enter. Oh no, not yet. I need my theta. Oh my goodness. Get on the ball, Mrs. Vibber. Negative 24. How is it negative? Well, because I obviously flip-flopped R1 and R2, because if I look back, I think my R1, yeah, it was that one. So I'm just going to ignore the negative and say that's 24.187. Alright, so we're at the end. We're going to do Star Wars jokes again today. So one Star Wars joke is, where do the Sith shop for school clothes? Where do the Sith shop for school clothes? At the Darth Maul. If you've watched the Star Wars, let's see, that would be episode 1. At the Darth Maul. And then this is an Empire Strikes Back one. What is the internal temperature of a tauntaun? What is the internal temperature of a tauntaun? Lukewarm. Ha ha ha. Alright, I'm done. Almost 20 minutes in. I'm sorry it's so long. You'll live. You'll survive because this is the last video. Yay!